mucho.
Introduce the first paper this afternoon by Kitayama, Asayama, Nomura, Sato, and Yamaguchi. Characterization of inner and outer surface of Sepiolite by positron annihilation. The paper will be given by Dr. Kitayama.
Good afternoon, ladies and gentlemen. Today, I'd like to talk about characterization of inner and outer surface of Sepiolite by positron annihilation. Positron annihilation spectroscopy gives the information from the core shape of nanometer size. Sepiolite has anisotropic nanometer size quartz, so we discuss here availability of positronium annihilation spectroscopy. First, I talk about crystal structure and thermal properties of Sepiolite. Sepiolite has an anisotropic intracrystalline tunnels. Sepiolite is magnesium silicate fiber, and ideal formula is indicated this form. As shown in this figure, magnesium hexahedral sheet and sandwich with 2 layers of silicate of silicon oxide layer, tetrahedral layer, and one block is formed in this unit. This is tunnel. The effective size of each direction is 10.5 angstrom, and the direction is 4.5 angstrom, and tunnel it is around C-axis, 5-axis. The thermal property is very interesting. Theoretic and coordinate water contained in this tunnel, and the sample heated at 393 Kelvin, theoretic water dehydrated and formed sepiolite tetrahydrate. The crystal structure is not changed, but however, tetrahydrate transformed to dihydrate by two water molecules dehydrated by heating 530 Kelvin. The crystal structure is changed and tunnel is folded. This table shows specific surface area change of sepiolite by heat. The sample contains theoretic water is smaller specific surface area than sepiolite tetrahydrate, and when two coordinated molecules dehydrated, drastic change of surface area is occurred. We use in this experiment sepiolite tetrahydrate was used. To observe anisotropy of sepiolite, we use well-oriented sample. This figure is the fiber of sepiolite oriented to fiber axis, and this produced in China. Positron annihilation spectroscopy has been known as new physical probes for studying the microporous materials. In contrary other technique, positron annihilation spectroscopy probes the free volume properties directly without significantly interfered by the bulk property. Now we would like to explain about positron. When positron is injected into the molecular substrate, it interacts with elastic collision process. In other words, it's excitation and ionization. During the slowing down process, and at nearly summarized stage, a positron may pick up an electron from the environmental material and form the bound state, so-called positron nu. Positron nu has different spin states. One is also positron nu. The also positron nu is a parallel spin state of electron spin and positron spin each other. Average lifetime is 114 nanoseconds. Parapositron is an unparalleled spin state of electron spin and positron spin each other. Average lifetime is 125 picoseconds. The positron annihilation is measured by angular correlation of annihilation radiation and positron annihilation lifetime spectrum. The schematic diagram of LCAR measurement, the source and sample, the source used copper-64 radioisotope setting in this phase, and this detector hits, and this detector moves at a constant rate. And LCAR measurement, the coincidence counts as a function of angle theta, the deviation from linearity of the two annihilation radiations. An LCAR spectrum maps out the moment of the annihilation positron. This figure shows an LCAR spectrum under vacuum and under 1 atmosphere nitrogen. Broad line is sample setting to perpendicular to the axis, and narrow one is sample setting to parallel to the fiber axis. Nitrogen is not affected the LCAR spectrum. LCAR curve is decomposed to Gaussian components, and this dotted line shows broad component, and this line shows narrow component. Narrow component is up in this figure. Narrow component parallel to fiber axis is narrower than perpendicular to the fiber axis. From the LCAR curve, PS component in 0-point motion of the center of mass in a cube is described by the following this expression. And the potential well of L is expressed by this equation. we decompose the spectrum of HCAR, decompose two components and narrow component analyzed by computer and calculation from SWHM and use this equation. The potential wave of 2L was calculated. This value is the nearly equal the tunnel size to the tunnel size of a direction of Sepiolite. And from the 2L value from calculated from the parallel to the fiber axis is smaller than expected value. This discrepancy is explained by the irregular orientation to C-axis of the fiber sample. Because we use natural sample and all of fiber is not completely oriented to C-axis direction. Therefore, SWHM of HCAR curve can be used to determine an effective radius of micropore. When 1 bar of oxygen as gas was introduced to the sample, isotropic HCAR curve was obtained. So the effect of oxygen absorption, we measure the lifetime spectrum. Typical lifetime spectra of Sepiolite and then in the vacuum and then the oxygen is shown in this figure. Long lifetime part is was changed. We decompose this part to 3 components: lambda rate time, lambda 1, lambda 2, lambda 3, decreasing the annihilation rate. First component is background plus parapositronium lifetime component, and the second part is pre-positron lifetime component, and third component is also positronium lifetime component. This figure shows positron-new annihilation rate as a function of oxygen pressure. Oxygen annihilation rate decreased drastically at the oxygen pressure 100 mm/Hg. Oxygen absorption isotherm was measured at room temperature to clarify abnormal behavior of positron annihilation rate. This figure shows the absorption isotherm of sepiolite at room temperature. This shows the sepiolite containing zeolitic water, and this shows sepiolite tetrahydrate. Its tunnels become empty to evacuate zeolitic water. Stepwise change was observed in this curve. This shows this point is about 100 millimeters. The change of lifetime and change of oxygen absorption started at nearly equal oxygen pressure of 100 millimeters as I took in lifetime step. Also, positron react with molecules and forms chemicals of fire. For example, substitution reaction and addition reaction and oxidation. Especially oxygen has large reactivity with positron, and positron oxide forms positron oxide. The lifetime of positron in sepiolite was prolonged by contacting the sample with oxygen gas more than 100 millimeters Hg. A drastic change of oxygen absorption may be attributed to the absorption of oxygen inside of the tunnels. Therefore, positron reacts with absorbed oxygen inside of the tunnels and form positron oxide. In absorption from absorption isotope, oxygen pressure less than 100 millimeters Hg auto-absorbed on outer surface of sepiolite, and oxygen pressure is larger than 100 millimeters Hg auto-absorbed on inner surface. And positron reacted with oxygen and formed positron oxide. From this result, we summarize. ACAR and positron lifetime measurements were applied to characterize micropore materials having diameter of 0.1 to 1 nanometer. ACR spectra of sepiolite were measured for parallel and perpendicular to the 5-axis. The anisotropic narrow component was observed in the ACAR spectra, and it reflected the shape of the tunnel in sepiolite. ACAR and lifetime spectra of sepiolite were not affected by gas absorption, helium, hydrogen and nitrogen, while oxygen have an influence on both ACAR and lifetime spectrum of Sepiolite. Especially, also positron lifetime was affected by oxygen absorption on Sepiolite. Drastic change of positron lifetime was observed at the oxygen pressure of about 100 mm/Hg, when the stepwise increase of oxygen absorption was occurred. Also, positron was stabilized by oxygen absorbed inner surface of tunnel. This means that also positron reacts with oxygen and it forms positron oxide compound in the inner surface and tunnel in Sepiolite.